Good afternoon, everybody. So, in my last class, I already told you the definition of normal. Okay. So, what is the definition of normal? Let V be an inner product space. T is a linear operator on V. Then T is said to be normal if T star equal to T star T. Okay. And also I told you an n+n real or complex matrix A is said to be normal if A star equal to A star A. So A star is nothing, this is just a conjugate transpose of A. That means A star is equal to, this is the A conjugate, then its transpose. This is the A star, this is the conjugate transpose of A. So if A star equal to A star A, then we will say that A is normal, matrix A is normal. So a linear operator T is normal if and only if its corresponding matrix, its corresponding matrix is TB, that is the matrix associated with this linear operator T with respect to basis or with respect to an orthonormal basis beta. So T is normal if and only if its corresponding matrix is normal. And also I did two examples, and first example is let T from R2 to R2 be a rotation theta. Let T from R2 to R2 be rotation theta, where theta lies between 0 to pi. The matrix representation of T is the standard order basis. The matrix representation of T in the standard order basis is given by A is equal to this one. That means T is a rotation or which is a linear operator on R2 is a rotation theta, and its matrix representation is given to you. The TB, this is the matrix representation A which is given to you. This is your cos theta minus sin theta and sin theta cos theta. So if this matrix TB or this matrix A, if this is normal, then this linear operator T is said to be normal. So how you will check its normal? So A is given to you, you can find its A star. So A star is just its conjugate transpose. So if you will find its conjugate transpose, this is in this way. So since it is real, its conjugate is the same one. Then what is its transpose? The first row will be in first column. So cos theta minus sin theta will be in first column. Similarly, sin theta cos theta, this will be in second column. So this is the A star. Then if you will calculate what will be your A star A and A star, then this will be your identity matrix I. So since A star A is equal to A star, so A is said to be normal. So if A is said to be normal, then A is nothing but the matrix associated with this operator T with respect to an orthonormal basis beta. If this thing is normal, then this corresponding linear operator T is said to be normal, because this thing holds T is normal if and only its corresponding matrix is normal. So if the corresponding matrix is normal, then T is normal. Okay. Then another example was here. So if A is a real skew symmetric matrix, given that A is a real skew symmetric matrix, then what will be your A transpose? Since it is a skew symmetric matrix, A transpose is your minus A. Then you have to show that A is normal. And then now you just find what is A star. A star means this is A bar transpose. So since A is a real matrix, so A bar is always equal to A. So A bar transpose means this is just A transpose. So now if you will calculate what is your A star A, so A star A means this will be your A transpose A, and A transpose is your minus A. Since A is a skew symmetric matrix, so A transpose is minus A. So minus A into A is minus A square. Similarly, if you will calculate what is A star, This is your A transpose, because A star is your A transpose. This is here. So A into A transpose, this is A into minus A, which is minus A square. So A star A is minus A square, and A star is also minus A square. So if we can say A star A is equal to A star, thus A is normal. So in my last class or yesterday class, I already completed these two examples. So now comes to a theorem. So what is the statement of this theorem? Let V be an inner product space let V be an inner product space and T be a normal operator on V and T be a normal operator T be a normal operator on V, then the following statements are true. Then the following statements are true. Okay. So what are the following statements? So in first bit it is given norm Tx. So norm Tx will be norm T star x. This is your first bit A. This is bit B. Then T minus Ci is normal for all C belongs to F. Therefore all x belongs to V. So whatever may be the S belongs to V, Tx norm is equal to T star x norm. Second bit T minus Ci, this is normal for all C belongs to F. That means C is any scalar. Okay. So then in third bit, if x is an eigenvector of T, if x is an eigenvector of T, if x is an eigenvector of linear operator T, then x is also an eigenvector of T star. Then x is also an eigenvector of T star. That means if Tx or T of x is equal to lambda x, then T star x is equal to lambda bar x. Okay, that means if x is an eigenvalue of T, then x is also an eigenvector of T star. And in D, what we have to show, if lambda 1 and lambda 2 are distinct eigenvalues of T, if lambda 1 and lambda 2 are distinct eigenvalues of T, are distinct eigenvalues of T. So if lambda 1 and lambda 2 are distinct eigenvalues of T with corresponding eigenvectors, with corresponding eigenvectors x1 and x2, then x1 and x2 are orthogonal. Then x1 and x2 are orthogonal. Okay. So now I will prove these 4 bits. Now comes to first one. The given thing is V is an inner product space and T is a normal operator on V. Okay, so these are given things for all these 4 bits. Given that V is an inner product space, and T be a normal operator on V. T be a normal operator. T be a normal operator on V. So in first bit, what you have to show? To show that norm of Tx is equal to norm of T star x. Okay. For all x belongs to V. So whatever may be the x belongs to V, then norm Tx will equal to norm T star x. So how I will prove it? Now consider Tx norm square. So what will be Tx norm square? This is nothing but the inner product of Tx with Tx itself. And if this T can be taken to this first vector, this is your first vector, this is your second vector, and this is the inner product of two vectors. So if this T will go to left side, or T from the second vector will go to first vector, then there will be a star. That means I can write this thing as T star of Tx inner product with x. And what is T star T? It is given that T is normal to you. So since T is normal, we know T star is equal to T star T. Okay, since T is normal, so in place of T star T, I can write this is T star T star of x comma x. So what is T star? Now I can took this T to the second vector. Then what will be this one? This will be T star x on first vector, and this T will go to that side. Then I can write this is T star x. Then T star x inner product with T star x. This is your T star x norm square. Okay, so what we got here? Tx norm square is equal to T star x norm square, implies if you will take the square root of both sides, then Tx norm is equal to T star x norm. So this thing proved. Now go to second bit. What you have to show in second bit? T minus Ci is normal, where C is any scalar. Okay, and the given thing is V is an inner product space. T is a normal operator on V. So these things are given to you, and you have to show T minus Ci is normal. Here, what we have to show that T minus Ci is normal. So T minus Ci is normal for all C belongs to A. Okay, so whatever may be the C, I have to show that T minus Ci is normal. So how to show that T minus Ci is normal? So T minus Ci is normal. That means we have to show that we have to show that T minus Ci star with T minus Ci, this thing is equal to T minus Ci into T minus Ci star. That means their products are commutative. This is the definition. If T is normal, then T star equal to T star T. That means the product of T with its star is commutative, or with its adjoint is commutative. So here you have to show this thing is normal, means this uh, T T minus Ci with its star, and if you will take their product, then this thing is commutative. So now consider T minus Ci star with t minus ci. So what will be t minus ci star? Since c is any scalar, so t minus ci star is t star minus c bar I. In the last class I already told to you this is t minus ci star is this thing. So this t minus ci star is this thing, then to t minus ci. Then what is the product? This is t star t, like distributive property. I will multiply this thing on this t minus ci. So this will be t star minus t, then t star ci, then this one on the right hand side I will multiply, then this will be okay. T star ci means this is c t star. I can write this thing as t star into ci. This is your c t. Similarly, c star I into t. This is your c bar t. Then c bar I into ci. Then minus minus is plus. Then this will be c bar c. So you know, since t is normal, given that t is normal, so t star is your t star t. So in place of t star t, I can write this is t star, t star minus c t star minus c bar t plus c bar c. So if you will take t star common here, then this will be t minus ci, and if we will take c bar common here, then this will be t minus ci. I can write here this I. So this is t minus ci. Then this is the t minus ci whole into t star minus c bar I. So this is your t minus ci whole into this is your t minus ci star. This implies your t minus ci star into t minus ci is your t minus ci into t minus ci star. Thus t minus ci is normal. Since these two products are commutative, so we can say our t minus ci is normal. Okay, now comes to third bit. So what we have to show in third bit, this is a third bit. If x is an eigenvector of t, then x is also an eigenvector of t star. That means if tx equal to lambda, tx equal to lambda means what? Suppose t is an operator and lambda is its eigenvalue and x is its corresponding eigenvector, then tx equal to lambda. So if tx equal to lambda x, then you have to show that t star x is equal to lambda bar x. So now what we will prove here. So given that x is an eigenvector of t, given that x is an eigenvector of t, x is an eigenvector of t, and what? So if x is an eigenvalue or x is an eigenvector of t, that means tx equal to lambda x for some scalar lambda, and x belongs to b. So if x is an eigenvector of x, then tx equal to lambda x for some scalar lambda, or this lambda is an eigenvalue. So if tx equal to lambda x, then tx minus lambda ix equal to 0. That means t minus lambda ix is equal to 0. Okay, so let u is equal to t minus lambda I. So if I will assume u equal to t minus lambda I, then u of x equal to 0 because u is this thing and u of x equal to 0. So if u is your t minus lambda I, then u of x equal to 0, and in the second bit or in bit b, we know that t minus lambda I or t minus ci, and c is any scalar and here lambda is a scalar. So t minus lambda I is normal. So we can write u is normal from b. Okay. So if you take u is your t minus lambda I, then ux equal to 0 and u is normal. This thing is proved in just in the last bit. So if u is normal, then from bit a you can say ux norm is equal to u star x norm from bit a. Okay. And what is there, since u of x is 0, so norm, from the property of norm, if u of x is 0, so its norm is 0, so norm ux equal to 0, and which is equal to norm u star x. So what is norm u star x? That u is this thing, so what is your u star? So your u star is t minus lambda I star. So t minus lambda I star of x. So what is t minus lambda I star? This is your t star minus lambda bar I of x. So what is t star minus lambda bar I? This is your t star x minus lambda bar x, lambda bar into x. This lambda bar is just a scalar. So t star x minus lambda bar into x norm, and this norm is equal to 0 because the left hand side is 0. Here given that lambda 1 and lambda 2 are distinct eigenvalues of t. Okay, lambda and lambda 2 are distinct eigenvalues of t with corresponding eigenvectors its corresponding eigenvectors x1 and x2 respectively. Okay, since and t is normal, it is given. And t is normal. An eigenvalue of t corresponding to this eigenvector x1. That means you can say tx1 or t of x1 is equal to lambda 1 of x1 and t of x2 is equal to lambda 2 of x2. And what we got in this bit C, if tx equal to lambda x, then your t star x is equal to lambda bar x. So here you can write but lambda 1 is not equal to lambda 2 because it is already given to you that lambda 1 and lambda 2 are distinct eigenvalues of t. See, given that lambda 1 and lambda 2 are distinct. Distinct means they are not same. Okay. So, but lambda 1 is not equal to lambda 2. Here lambda 1 is not equal to lambda 2. But lambda 1 into this thing is equal to lambda 2 into this thing. So this is only possible if inner product of x1 comma x2 is 0. So if this thing is 0, then lambda 1 into 0 is 0 and lambda 2 into 0 is 0, then both are equal. So here you can write, but lambda 1 is not equal to lambda 2. Hence we conclude that inner product of x1 with x2 is equal to 0. Thus x1 and x2 are orthogonal. Then x1 and x2 are orthogonal. Okay. So now proof of this theorem is completed. Now I will see only the statement of another theorem. Only the statement. Let T be a linear operator. Let T be a linear operator. Let T be a linear operator on finite dimensional